Dear friends, welcome to Infos. Welcome to another video from Infos, another video from oil and gas training series, heat exchanger part 5. In this video, we are discussing about corrosion and fouling problems in heat exchangers. So, various operational problem and environmental problem, corrosion problem, fouling problem, etc. etc. So, heat exchangers are valuable equipment, costly equipment. So, maintenance of heat exchanger is a costly business. So, we have to keep the environment, heating fluid, material selection, etc. etc. Everything we have to take care of to maintain or preventing corrosion or preventing fouling and to get a best result from heat exchanger. So, we will discuss this one, what is corrosion, what is fouling, and what are the various factors there, and what are the method for minimum maintaining or preventing corrosion and fouling. Welcome to this video. So, as you know, corrosion is a general phenomena in the plant, in the hydrocarbon operation system or hydrocarbon operating plant, not only in heat exchanger, but heat exchanger also we are discussing in heat exchanger today here. So, corrosion is a form of damage that metals can experience when in contact with certain environment. Corrosion causes the metal to degrade, which can lead to reduction in strength and leaking. There are numerous corrosion forms, and the type of corrosion is a component experiences is depend on the environment, material and design of the system. So, simply it is weakening the material, so weakening the metals, and later stage it cannot perform as per the design condition, and it started leaking in case of heat exchanger or in the pipeline. So, various forms of corrosion is there. We are not going to discuss it in detail corrosion. You can Google it, that one, understanding various form of corrosion and how it is happening, and the prevention methods are there using in oil and gas operation. Cathodic protection is one method. So, details you can get it in Google, or I can take it a class in a later stage what is cathodic protection. So, we are coming to our point, corrosion in heat exchangers. Excessive fluid velocity on either the shell side or tube side of the heat exchanger can cause damaging erosion as the tubing metal wear. If the corrosion is already present, it can be accelerated. Erosion has the potential to remove the tube material's protective film, exposing fresh metal to further attack. So, excessive fluid velocity. So, there are various factors are there to affect corrosion, and not only one fluid behavior. No, fluid chemistry can affect because of the viscous fluid or light density, different chemistry of the behavior of the fluid. A fluid or a metal temperature, it can affect on corrosion, creating corrosion in the shell side or tube side. And third one is a fluid flow rate also. In general, this is talking. And heat transfer performance of heat exchanger affected by many factors, such as the opening temperature of the heat pipe, the rate of fluid filled, the physical nature of the liquid refrigerant or liquid, you can say in fluid, the work temperature of the tube, angle, tube spacing, tube length, hot and cold fluid flow, and wind speed. These are the factors affecting on the performance. At macroscopic level, thermal conductivity largely depend on three main factors: operating temperature, moisture content, and density. Other factors are thickness, pressure, air surface, velocity, and aging. So, these all factors in general, where we are talking that one, in all these factors are affecting performance of the heat exchanger, plus contributing some level of corrosion in heat exchangers. So, corrosion factors in detail again coming: material selection, material coating, material thickness. These are no need further discussion on that one. Metal working, foaming or welding, impingement attack, maintenance or cleaning frequency, drain and dry heat exchangers when not in use, and that means in shutdown time or partial shutdown and long time shutdown, short shutdown and long time shutdown. That is meaning for drain and dry heat exchangers, fouling that we will discuss in a coming slide, film formation, etc. So these are the common factors which can affect or lead or accelerate corrosion in heat exchangers. Type of corrosion is explaining galvanic corrosion is common in shell and tube heat exchangers, and the contacts between the tubes and the baffles or tube sheet when different metals are used in for those spots. Galvanic corrosion, also called dissimilar metal corrosion or wrongly electrolysis, refers to corrosion damage induced when two similar materials are coupled in a corrosive electrolyte. It occurs when two or more dissimilar metals are brought into electrical contact under water. So these are about galvanic corrosion. So the studies are telling that when heat exchangers are experiencing generally galvanic corrosion. Pitting corrosion is most likely to occur during shutdown periods when there is no fluid flow and the environment is most suitable to build up concentration cell. These are some pictures available in pitting corrosion. These are the general pictorial representation for the corrosion examples on heat exchangers, various heat exchangers available in Google. So cost of corrosion is, we have to consider that part also. Cost of corrosion is always more significant than just the replacement of heat exchanger or element. Process downtime, change out cost, accessing the equipment and pressure testing are all additional cost of corrosion. These high losses are a combination of direct and indirect cost caused by corrosion and can be attributed to several economic consequences as follows: replacement of corroded equipment, oversizing to take possible corrosion into account, preventive maintenance, shutdown of equipment, loss of efficiency. For example, when corrosion product decreases the heat transfer rate of heat exchanger, loss of product, example through leakage or contamination of product. So these all are contamination is product also very important issue. So these all are costing in a higher level due to corrosion. So that also we have to consider. So fluid selection, general heat exchangers fluid selection to preventing corrosion and best performance in shell and tube heat exchanger. Some general rules are providing here. In tube side, always this is the heat exchanger picture here. So this is the tube side entry, this is the tube side entry and tube side exit, and shell side entry and shell side exit. So in the tube side, we prefer always fouling or erosive or corrosive fluid. So toxic and lethal or valuable fluid, fluid at a greater pressure, hotter fluid with a less available pressure drop, less viscous fluid with similar volumetric flow rate or cooling fluid. So these are always we are preferring in tube side. The reason is a corrosive fluid means we can find out easily, the tube we can replace easily, and high pressure fluid means any pressure leakage, tube leakage is there, shell side pressure will increase quickly and tube side pressure will decrease quickly. So we are always installing in the tube side pressure gauge for local and pressure transmitter for remote reading and indication, and shell side also we are keeping temperature and pressure gauge both tube side and shell side. So then we can easily indicate, monitor the performance of pressure and temperature performance of the heat exchanger, and quickly we can get an idea on any abnormality happening in tube side and shell side. So many other reasons are also there. In the shell side, normally vapor forming inside the heat exchanger fluid should generally be allocated in the shell side because they have a larger volume and a lower heat transfer coefficient. Fluid with higher flow rate is generally preferred to the kept on the shell side. These are the fluid selection in general. I kindly request you to see your heat exchanger operating and what is the condition of fluid behavior and fluid selection process, how it is done. Just to check it with that one. Another, how do I know when I have a heat exchanger failure? So mainly heat exchanger failure, to understand that one, tube side temperature performance, tube side pressure performance. Tube side means inlet, tube inlet and tube outlet. We are providing instrumentation like pressure sensor and temperature sensor and pressure reading, pressure monitor, indicator and temperature indicator. So from that one we will get some information here. That's why I have added here a instrumentation drawing here. See, this is the tube side inlet, tube side outlet is there, and shell side inlet is here, shell side outlet is there. Some of the reading you can take here. See, TT is here, and here we can put a TI. So shell side we put PT. Here also we can put, so various instrument you can put here and take the reading from that one. We can primarily we can monitor. Initially we can monitor, the first line monitoring is possible in heat exchanger. Then we can call the heat exchanger specialist people, mechanical or other type of people, to find out pressure test or inspection. Various procedures are there as per international codes. So we can do that one. So tube leak, how to get info? Pressure increase in the shell side and the tube pressure will decrease. So shell side pressure will increase, tube side pressure will decrease. That is one way. So heat transfer not efficient or decrease temperature on shell side or tube side. So that is also another way to understand that. So heat transfer performance using by temperature and pressure, we can first line information will be available. So how can I improve the life of heat exchanger? Routine inspection and maintenance enable you slow the degradation effect in heat exchangers, and monitoring the temperature and pressure flow rate also, continuously monitoring that one, that also can maintain the corrosion level at minimum. The effects will always be present, however, and will sooner or later the result of necessity of replacing degraded components. So preventing corrosion or minimizing corrosion, we can say better. Choose the right material for water condition. Plate design heat exchanger material stainless steel. Tube and shell design heat exchanger 99% of pure soft copper or copper nickel, or an alloy of copper that has 10% nickel. Enhance heat exchanger life to add zinc anode to the heat exchanger bonnet. Zinc anode adding is sacrificial anode, so it will corrode first. So time to time adding zinc anode to preventing heat exchanger corrosion. That also one way to minimize the corrosion. We cannot 100% stop corrosion. We are maintaining, or we are preventing or maintaining minimum corrosion in heat exchangers. Preventing corrosion, keep your water supply clean, or water treatment you can do that one. Water quality you can maintain, always lab analysis or chemical water quality analysis you can conduct. Environment should be improved, dusty or windy or dirty environment you can make it clean. Monitor or the cooling fluid flow rate. Protect your heat exchanger during shipping or storage. Regular heat exchanger maintenance, monitoring and maintenance. That is very, very important. So next is heat exchanger fouling. This is simple representation of heat exchanger fouling. So fouling is the formation of unwanted material deposit on heat exchanger surface during process or heating and cooling. It occurs in all industries and most heat exchanger design, with impact ranging from heat transfer degradation to flow resistance and pressure drop. Fouling increases the overall thermal resistance and lowers the overall heat transfer coefficient of heat exchanger. Fouling also impedes fluid flow accelerates corrosion and increases pressure drop also in heat exchanger. Across the heat exchanger. So fouling definition is type of fouling you can say in crystallization fouling. One type, this is caused by salt that dissolve and crystallize upon cooling. Consider shell and tube designs for fluid with high salt content subject to high temperature changes. Sedimentation or deposit of sand, rust and other compound in heat exchanger. Sedimentation comes from the corrosion product, metal oxide, silt, alumina and diatomic organism like microalgae, and their excrement. Velocity adjustment can be made in some cases to reduce the impact of sedimentation. So, adverse effect of fouling: increase the capital cost due to larger equipment, additional energy required due to a increased pumping or a reduction in energy recovered, maintenance cost of chemical treatment and cleaning, loss of throughput, downtime cost. These are the adverse effect in this fouling. So these are the simple two photos available in fouled tube bundle. Categories of fouling, some quickly we can brief that one. Particulate fouling, biofouling, corrosion fouling of tube material, participation or scaling fouling in because of the cooling water or something, chemical reaction fouling, coking. Generally several fouling mechanisms occur at the same time, nearly always being mutually reinforcing. So these all are the general particular reasons are there. You can say chemical reaction and biofouling because of the algae, and precipitation or particulate, like different type of in a micro level we can say that one different type of fouling is involved in heat exchanger. Particulate fouling, accumulation of finely divided solid suspended in the process fluid onto the heat transfer surface. In some time setting by gravity prevails sedimentation fouling. Frequently semi superimposes on precipitation and facilitates certain type of chemical reaction fouling. This is the pictorial representation available in Google. Biofouling, you can say this is organic, this one, attachment of macroorganism or microorganism to heat transfer surface plus adherent slims often generated by the latter, combined with or superimposes on precipitation and particulate fouling. Degree varies with water source and season. Bacterial growth can usually be controlled by chlorination. Another one, corrosion fouling. The heat transfer surface itself react to produce corrosion product which foul the surface and may promote the attachment or other foulant. Heavy hydrocarbon stream at a temperature of about 290 degrees C or higher cause corrosion of carbon steel tubes and other components due to high temperature sulfur corrosion. So this is another type of corrosion. Another type of fouling, corrosion fouling. So precipitation fouling, the precipitation of dissolved substances on the heat transfer surface. In particulate fouling, it is undissolved solvent. Here it is a dissolved substance. With the inverse solubility of salt, the precipitation occurs in superheated rather than subcooled surface like scaling. So chemical reaction, it is a reaction between the material and the fluid, or heating fluid or cooling fluid, or the contaminants. Deposit formed at the heat transfer surface by chemical reaction in which the surface material itself not a reactant. Such fouling result a oil sludge, organic polymer or insoluble decomposition product. Surface temperature very significant. Coking fouling, although generally used to describe many forms of organic fouling, coking typically occurs high temperature in crude and middle distillate service. Foulant materials have high organic content and appear as a black oily deposit. Rate of coking is a function of tube wall temperature and the amount of fouling precursors like asphaltenes present. Parameter which affect fouling: fluid velocity, like high velocity minimize all modes but require more pumping power. Wall temperature affects scaling, biofouling, chemical reaction rate, nature of fluid and tube material. So these are the parameters which affect fouling. So the stages of fouling, you can say step 1, 2, 3, 4, 5, general informations, initiation, delay, nucleation, induction, incubation, surface conditioning, transport, that is mass transfer, attachment, surface integration, sticking, adhesion, bonding, then removal, release, re-entrainment, detachment, erosion, spalling. Step 5, aging. So these are the stages of fouling. It is starting from the initiation to like it is permanently aging, that fouling. How fouling is built up? So there is a simple graph showing fouling resistance versus time. See, the initiation period is there, then it is this is the time, and it is coming down, then it is moving by linear way or falling way or asymptotic way. This three-way fouling is taking place in heat exchanger surface. Reference delay time also they are providing that one. So how to provide fouling allowance? Cleanliness factor, steam surface condensers, percentage additional area, does not distinguish between shell side and tube side. Fouling resistance, not fouling factor. Fouling resistance should cater only the fouling and not to uncertainties in design, future plant capacity increase, etc. So some fouling allowances providing by design people for giving allowances for fouling. So design guidelines for minimizing fouling. Use heat exchanger type that foul less, plate, spiral, fluidized bed, helix edges and twisted tube. Tube side easier to clean, tube side. Hence dirty fluid always prefer in tube side. However, dirty fluids invariably more viscous than it will put into shell side. So dirty fluid on tube side, maximum fluid velocity within erosion limit, cooling water 1.3 meter per second minimum. Use bigger diameter tubes, 20 mm, 25 mm, even bigger. Check pressure drop with fouling layer thickness or leave sufficient margin. Use spare handle, spare shell, use spare bundle or spare shell. Use two shells in parallel, each 60 to 70%. Use tube insert, minimize fouling to dramatic level. Use chemical additives, antifoulants. Use online cleaning. So these are the fluid selection, fouling fluid selection in tube side, plus the prevention of fouling in a minimum level. Dirty fluid on shell side, use floating head or U-tube design, use a square or rotated square layout, minimize dead spaces by optimum baffle design, maintain high velocity, use multiple shells in series. So see, shaded areas indicate potential high fouling areas. See, the flow is going, these areas are fouling. So these are the general information on fouling and corrosion. So just to you will get a chance to visit a mechanical workshop and a process area to understand the fluid conditions, behavior and instrumentation monitoring the performances and mechanical activities on heat exchangers. So thanks for watching this video. I hope we have complete almost general or basic or elementary information on heat exchangers. So I am planning to start with a new subject that is important in oil and gas operation, pump. So next week onwards we will start a new subject, new video on pump operation and maintenance or characteristics, definition, etc. Thank you for watching the video. Thanks for all support and giving this time, and request you to watch all of my videos. That link I have providing in I'm providing in description area. So have a good day.